Let's pick up where we left off. In this video, we're going to introduce the concept of the Fourier series using the example that we've been working already. So, up until now, we've taken a periodic signal with a period of 10 seconds, and we have attempted to express what cosines lie within it. And I think we're arriving at a formula or a theory now that we can state openly. And specifically, what we've discovered is that for some periodic signal, x of t, with period t, we can express x of t as a sum of cosines. Let's see, as a sum of cosines, I'm going to write this sort of pseudo-mathematically. As a sum of cosines, and the frequency of those cosines will be integer multiples of 2 pi over the period, and the amplitude and the phase will be given by the nth value of a. Let's see, so a sub n was given by the inner product integral, and is equal to k sub n over 2 e to the j theta sub n. So this will be theta sub n, k sub n, and we're going to sum from n equals 1 to infinity. That's actually mostly true. Let me make it 100% true. In order to make that 100% true, we need to start our sum at 0, but we're not going to sweat that detail in this video. We'll do the n equals 0 is a special case, and we'll do that in the next video. That's kind of what we worked out so far. You can start with the first harmonic, which you can see here. We did when n equals 1. And then we add the second and the third and so on. And then the more harmonics you do, the more your sum of cosines will converge to x of t. So that's all well and good. All I want to do in this video now is to introduce the concept of the frequency plot. So let's talk about that. So in order to get the frequency plot, I'm literally just going to be plotting the magnitudes and the phases of the different values of A versus frequency. So let's just try by example. So in this case, let's see, I'm going to draw let's start with the magnitude plots. So here we have frequency, and I guess I'll do it versus radians per second. And it looks like my first frequency is going to be at 2 pi over 10 radians. Let's see, 2 pi is about 6, so about 6/10 of a radian, give or take. So we'll say 2 pi over 10, that's about 6/10 of a radian. Sorry about that. And we can see that the amplitude there is 0.0984. So I'll just draw a stick, and we'll label that 0.0984. Good. Now the second frequency we have is double the first frequency. So we can just space it out. That's going to be at about, let's see, 4 pi over 10 radians per second. And its magnitude is going to be almost the same as the first one, maybe just a hair less. So let's draw that. Okay, I'm not going to bother writing the values. And then we'll do the third one is here. This is a frequency of 6 pi over 10. That's the n equals 3 term. And that magnitude is a little bit less than the ones that come before it. That's about 0.8, and then so on. So in the previous video, I stopped my hand calculation at n equals 3, but that doesn't mean that there's not more numbers, right? In fact, we need infinity of values. So this plot really goes on and on and on. Okay, so this is the magnitude of A. Let's just call that the magnitude of A. Now separately, there's going to be a frequency plot, and same thing, j omega, it's going to be the same frequencies, 2 pi over 10, 4 pi over 10, 6 pi over 10, and the phases are going to be -2, positive 1.8, and minus 0.3. All right, and there you go. That's your phase angle of A. Now, again, there's more of these, and doing these by hand is going to get old pretty fast. So what we're going to do is we're going to use a computer to flesh out this plot for us. Also, before I go on, keep in mind that technically speaking, we also have the mirror image of these plots for the negative j omega axis. But again, as we discussed earlier, we're not going to plot those just out of just to keep the plots simple. So let's go ahead and create our plots. Here's the code that we used in the last video. So I'm going to use that as a starting point. Here's my formula for A. Let me just cut and paste that. So let's see, clear. And I'm going to redefine the, let me just put a dot here. We'll get to the dot later. Okay, so so the way we had defined A before is that we could do A of 1, we could do A of 2, and so on. But another thing we could do is we could say, let's see, something like let I equals 1 to 10. And so I is a vector from 1 to 10. And then we could say, give me A of I. And then we'll get all 10 values of A of I. Okay, so we'll get A of 1, A of 2, all in one go, which is super convenient. So here's what we're going to do. We're going to say I equals 1 to 25. We'll look at the first 25 harmonics. Look at first 25 harmonics. Then we're going to define our values of omega. So omega equals 2 times pi over 10 times I. So now we're going to get one value of omega for every value of I. So omega will have 25, will also be an array of 25 values. So this is going to be our frequency vector. And then finally, we're going to define our values of A. Now we have to be a little bit careful here because I've already used the letter A for the function name. So I don't know, why don't I do something super uncreative like AA? I'm not real happy with that, but it'll do for now. So that will be A sub I. And now I'm going to go create my plots. Again, it's frequency on the x-axis and then either magnitude or phase on the y-axis. So let's do figure 1. And now I'm going to use the subplot command. And what that's going to do is, well, you'll see in a second once I plot it. Let's see, let me just do this first. Stem, see, is that going to work? It is going to work. Okay, so what you can see here is that when I used the subplot command, it broke the figure window into one row and two columns. So this is the first column, and then this unused spot is the second column. And then I said I would like my plot to go in the first of those spaces. So that's, here it is over here on the left. And I'm saying create a stem plot. I'm using stem instead of the plot command because I want this little lollipop plot action. And I'm saying put frequency omega on the x-axis, and I'm saying put the magnitude of our Fourier series on the y-axis. Okay, and if I want to get really fancy, I can say something like x label frequency in rads per second and title magnitude. Okay, so now my plot's properly labeled. And you can see right off the bat that the hand plot we created is pretty much correct. Here I have my, let's see, that should have been, where is it? We should have had 0.0984, 0935. And here's your 0984, 0935. So that's good. These are roughly the same values as, not roughly, they're exactly the same values as we saw before when we did the hand plot. The nice thing here is that I didn't actually have to do any hand calculations to create this plot. I just let MATLAB do the work for me. So now I'm going to create the phase plot. So I'm going to issue the subplot command again. So again, I want to take my figure window, break it into one row and two columns, but now I want my plot window to go in the second slot, so I've changed that to a 2. And I want to do still frequency on the x-axis, but now I want to do angle on the y-axis. And this will be phase in radians is my title. And there we go. It's a little bit jumbly, not really sure what to make of that, but there it is. So let's go ahead and copy the figure, put it back in our window here. And oops, let's talk about that for a minute. See what we can learn here. So what you can see is that a couple things that are interesting. If we just focus on the magnitude plot for a second, what you can see is that most of the energy is at lower frequencies. As we go up in frequency, there's less and less energy, sort of like diminishing returns. So most of the shape of the signal is determined by the lower frequencies. And then as you get to higher frequencies, they sort of contribute less and less. And in fact, if we had, instead of going to 25 harmonics, what if we had done something like something daring, like let's say 100 harmonics? Okay, you can see that that pattern gets even more intense, right? So the higher we go in frequency, the less the less contribution those higher frequencies contribute. Which isn't to say that they're not important, those higher frequencies. They absolutely are important. It's just that we're they sort of become less and less valuable. Okay, so that's how we make our first frequency plot.